relation. Okay. So now we're going to write potential energy and work done by conservative force. Work done by conservative force. Force relation. Okay. So what is this? So consider gravity. If you have an object, if it is raised to height h, if it is raised to height h, the object is raised to height h, then how much is the increase in its potential energy? Delta U. Is it mgh? The increase in potential energy is mgh. Now, what is the work done by gravitational force? So gravitational force, the mg is acting downward and object is going upward up to height h. So the work done will be minus mgh. Okay. As the object is going upward, the change in potential energy is mgh, and similarly, the work done by gravitational force is coming what? Minus mgh. So what we can say is the change in potential energy is equal to negative of work done by gravitational force in this case. Okay, so this is for gravitational, for gravity. For gravity, this is the example that we are getting the change in potential energy equal to negative of work done by force. Similarly, we can take another example for spring. For a spring, if you see what is happening in case of spring, if a spring is here, okay, if it is initially relaxed, initially x equal to 0. Okay, so if it is pulled by some external force, so what will be work done by spring? So if it is pulled by external force, the work done by spring is, if you pull it, the work done by spring is what? The spring force is acting in backward direction and displacement is in forward direction. So work done by spring is minus half k x square if it is pulled by distance x. So final x initial is 0 and x final is x. Okay. So if it is pulled by distance x, the work done is minus kx square. So this expression we have already derived in the last class. And the work done by spring force is this. And what will be the potential energy? As it is stretched, there will be increase in potential energy of the system. Okay, so potential energy of the system will increase. So whatever work we did on this spring, the same work is getting stored in it as potential energy. And if you release that spring, that work is going to again deliver to some other system. Okay, so the potential energy change in this case we can write as half kx square. So again these two are becoming like this, means w equal to minus delta u, or minus delta u equal to w. So delta u equal to minus w. Okay, so what we can see is that there is a relation between the work done by conservative forces and the change in potential energy due to these conservative forces. So the thing which I was saying, that we can associate something at this point A and B, and for finding the work done, we can directly take the difference. So that thing is actually negative of potential energy. So if you want to find work done between A and B, if you want to find suppose work done between A and B, the Wg, you can simply take the negative of potential energy change. That will give the work done. Okay. So this is the relation between the work done and conservative force. Work done and conservative force. So in this way we can write. So now we can elaborate this further. So we can take this to next step. So delta U we can write as minus work done by a force is how much? Work done by conservative force. So I will write it C. So C means work done by conservative force. So this is work by conservative force. Okay. So next I can write it as Next, I can write it as, since work done we define as force dot displacement. So we can write it like this. Okay. So integration of conservative force with negative sign gives the change of potential energy. Integration of conservative force with displacement gives the change of potential energy. Okay. So we can use this relation to find some potential energy. So I gave example of a spring force and gravitational force. I can take some other example also. So I am giving an example. So this is from work to potential energy. From work to potential energy. Okay. So we will take an example. How do we use this? So suppose we have a force 2I cap 3x j cap and 4k cap. Okay, so this force is there, and we have to find the potential energy or potential difference. This is what? This is the potential energy difference. This is the what? Potential energy difference. Okay, this is potential energy difference because delta is kept there. So we are writing all the things in terms of difference. So suppose we are provided with this force, find the potential energy difference between points. Find potential energy difference between points 1, 1, 1 and 5, 6, 7. Okay, so what is happening that a particle is moved from these 2 points, means from point 1, 1, 1 to 5, 6, 7. So a particle is suppose moved from point this to this. So we have to find the potential difference. Okay, so how do we define potential difference now? So potential difference U, delta U will be equal to FC dot ds. Okay, with negative sign. So we can write like this. And how much is FC? FC is 2I cap plus 3x j cap plus 4k cap. Okay, and dot ds. So ds is how much? Ds, the displacement we can write as ds is written as this: dx I cap, the x direction displacement in I cap direction, y direction displacement in j cap direction, and z direction displacement in k cap direction. So it will be dx I cap, dy j cap, and dz k cap. Okay, so after taking dot product, if you take dot product, the 2 dx, okay, and then okay, here do not take this 3, otherwise it will become non-conservative. I am giving you okay, modify the question little bit, take it 2x here instead of x here, take x here. Okay, at this point, so take x here. Why I changed this? Because if you put x here, this becomes non-conservative. So I will discuss those things later, but for now consider this as a question. Okay, so 2x dx and 3 dy, then 4 dz. Okay, like this, and put the limits. So what are the limits? Limits are, see, particle is starting from point 1, 1, 1 to 5, 6, 7. So limit on x. So x is changing from where? From point 1, coordinate 1 to coordinate 5. So x, limit on x we have to put here because this is integration. So 1 to 5. Okay, then limit of y 1 to 6. 1 to 6. Similarly, limit for z. So for z 1 to 7. Okay, so these are the things you have to do, and then there is a negative sign with the whole. Okay, so these things we have to solve to get the kinetic energy. So we will have x square 1 to 5, then 3y 1 to 6, then 4z 1 to 7. So it will be minus, and how much value we can put? So x square minus 1. So 5 square minus 1 square plus 3, 6 minus 1 plus 4, 7 minus 1. So how much do we get? We will have 25 minus 1, that is 24. Then we have 5 into 3, 15. Then we have 6 into 4, 24. So how much total we are getting? We are getting 48. So 58 plus 5. So 63. Minus 63 we are getting. So this will be the potential. So whatever unit we take, I have not written units here. So if you write in joule or meter, then you will in Newton and meter, you will get this answer in joule. If you write this one as Newton and this as meters, then this will be in joule. Okay. So in this way, we find the potential difference between different points. Means like this we can find. So this is with the help of integration.